Welcome everyone to DuQIS event with Dr. Jimmy Chen from Google. Dr. Jimmy Chen is a senior research scientist in Google's quantum hardware group. He completed his doctoral degree at UC Santa Barbara and his undergraduate degrees at the University of Minnesota. His current research focuses on collaborating and benchmarking high fidelity quantum gates and quantum measurement in superconducting qubits. I'm today's host. If you have any question, just drop it in the chat. I think Jimmy will also stop at some point to ask if there are any questions. So just feel free to ask. There's also going to be a Q&A session after the talk is over. Just feel free to ask anything. Today's talk is about beating a classical computer with a superconducting quantum processors. We'll just see how Jimmy will show the world about quantum supremacy.
Okay, great. Thank you, Nora. Thank you so much for the invitation and setting this up. It's my pleasure to be speaking virtually with you guys at Duke today. So as Nora mentioned, I'll be talking about some work that we did about a year ago now. In the pandemic, it's a little bit hard to gauge how long time it is, but it really has been a year, where we demonstrated beating a classical Schrodinger, it's just a supercomputer with a superconducting quantum processor. So yeah. Before I get to sort of the meat of my talk, let me tell you a little bit about our group at Google. So at Google, we have sort of two missions in quantum computing. The first is that we want to develop quantum hardware, which are programmable devices which behave according to a simple quantum model. And the second thing is we want to develop quantum algorithms to leverage this hardware to solve certain computational problems that are hard for classical computers. And to achieve these missions, we're located in three primary locations. The first is in Santa Barbara, California, which is where the actual sort of experiment and the computer live. That's also where I work myself. We also have a team in Venice and Los Angeles who work on sort of theory and algorithms. And finally, we also have team members in Seattle who sort of work on our cloud infrastructure and software. Okay, so I want to start with just a little bit of history first. So the sort of idea of quantum computing comes about in the late 70s and early 80s. And one of the early proponents or evangelists is a physicist by the name of Richard Feynman. And I will never be as eloquent as Feynman, so I'm just going to quote him here verbatim. He says, "Nature isn't classical, damn it. And if you want to make a simulation of nature, you better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy." And that's sort of my emphasis there on the doesn't look so easy part. So people thought this was sort of a neat idea, but the rush to really try to build one of these things really comes after discovery in 1994. So a computer scientist by the name of Peter Shor discovers an algorithm to factor a large integers on a hypothetical quantum computer in polynomial time. This is a big deal because a lot of sort of encryption relies on factoring, the hardness of factoring these large integers. And this really spurs a lot of the research that's continued on to today in trying to build a quantum computer. So in the 20 years since Shor's algorithm was discovered, we've made a lot of advances in what's now called quantum information science. So on the experimental side, we've realized prototype quantum processors in a variety of different platforms, including trapped ions, the superconducting circuits I'll be talking about today, as well as more exotic things such as defects in diamond. On the algorithm side, we discovered additional algorithms, and aside from just Shor's algorithm, including unstructured search or Grover's algorithm, which you might have heard of, optimization, and what's really been popular recently is quantum chemistry, or using a quantum computer to simulate chemical processes. But throughout all of this research, I'd say up until maybe last year, I'd argue, there was a really big question, which is that, can we build a real quantum computer which outperforms today's classical computers? And there's real doubt that this could be done. First of all, the quantum computers we're building, even the one that I'm going to talk about today, are very error prone. And so as you can see, the meme I've got there is that the qubits are few and they're very full of errors. And as we try to increase the number of qubits, the complexity of these systems increases, and the number of ways that errors can come in also grows. So we really need to do sort of large-scale systems tests of real systems to see if they'll perform as we expect. And finally, there was always the specter that new physics might come in if we build a large enough quantum system, which might even in principle prevent quantum computing. So the sort of effort to try to demonstrate that a quantum computer can beat classical supercomputers was dubbed quantum supremacy by a professor named John Preskill at Caltech in 2012. I will mention that quantum supremacy is a term that came about 8 years ago, and that's also how we refer to this task up until last year. But I think in sort of light of recent events, we've also reflected a little bit about whether this is what we really want to refer to this task. And for the rest of this talk, I'll generally refer to this as either beyond classical or trying to beat a classical supercomputer. But nevertheless, John Preskill sort of lays out that one of the really important milestones is to try to demonstrate that a quantum computer can beat ordinary digital computers. He says something else, though, in this introductory lecture, which really resonated with me as an experimentalist. And he asked the question, is controlling large-scale quantum systems merely really, really hard, or is it ridiculously hard? And what I hope to show you today is that controlling large-scale quantum systems is only really, really hard. Okay, so here's an outline for the rest of my talk. I'll begin with a lightning introduction to quantum computing. I'll then talk about what Google's approach to building quantum computers is. I'll talk about exactly what this task is that we want to use to try to demonstrate beyond classical performance on a quantum computer. And then I'll show you the data that we actually perform this task. Okay, so I want to build for you a sort of model for quantum computing. But before I do that, let's build a model for a classical computer. So computing is all about manipulating information. In a classical computer, we need a physical representation of that information. Here I've sort of drawn light bulbs that are either on or off, but in a real computer, that might be the state of a transistor, for example. We then need an abstract representation of that information. In classical computing, we use the numbers 0 and 1, or classical bits. We need a way to manipulate this information. And at the sort of most basic level, you can write down a sequence of Boolean logic gates where each logic gate transforms the bits in a certain way and put these logic gates together to form what's called a logic circuit. And finally, at the end of the day, what you get out of the circuit, you have to be able to read it out and actually, say, what is the information telling you at the end. So these are all the ingredients that we're going to require for our quantum computer. So let's start with the physical representation. So probably the most simple quantum system that I can think of is the electron. Now, quantum mechanics tells us that if I put these electrons in a magnetic field, and if I measure something called the electron spin, it's either going to point up or down. So these are two discrete states that we get out of the electron that are sort of quantum mechanical. And just like in classical computing, I can assign numbers 0 and 1, and I form what's called a quantum bit or a qubit. So two possible quantum states here. Now, quantum mechanics also allows us to write down other states of the system. And the way we do that is by assigning a complex number to each of 0 and 1. And this forms what's called a quantum superposition. And you can think of this sort of more general state as a complex combination of 0 and 1. And the meaning of these numbers, C0 and C1, or we also call them amplitudes, is that the square of these numbers, it gives us the probability of measuring the system in either 0 or 1. So ultimately, these quantum bits are probabilistic. Now, this abstract representation is sort of a mathematical formalism. In quantum computing, we like to use a more visual representation of the system using something called a Bloch sphere. So on the Bloch sphere, the North Pole, let me turn the pointer on real quick here. The North Pole here represents the 0 state, the South Pole represents the 1 state, and all the other possible states in the system are represented by various locations on the surface of the sphere. So for example, on the equator here are all the sort of equal superpositions of the qubit, where we have the 50% chance of measuring 0 or 50% chance of measuring 1. And the various states along the equator are different sort of proportions of real versus complex, for example. So this has a really nice physical interpretation when it comes to talking about the electron, because it corresponds to classically what direction the spin of the electron will be pointing. But we can also use this sort of abstract Bloch sphere to talk about any sort of qubit, whether that be trapped ions or superconducting qubits, for example. Okay, so that's a single qubit. Now let's talk about what happens when you have multiple qubits. If I have a single classical bit, I need exactly one number to represent that, either 0 or 1. And I've just told you that for a quantum bit, we actually need two complex numbers. If I have two classical bits, now I need two numbers that are both either 0 or 1. But in quantum mechanics, we have a phenomenon called quantum entanglement, which says that if I measure one qubit to be 0, that has a non-trivial correlation with the measured state of the other qubit. And what that ultimately boils down to is that I actually need a complex number or amplitude associated with each one of the classical possibilities, 0, 0, 0, 1, 1, 0, and 1, 1. In other words, I actually need 4 numbers for these two quantum bits, where each of these amplitudes now corresponds to the probability, for example, of measuring 0, 0. And if I have 3 classical bits, I need 3 classical numbers. But if I have 3 quantum bits, I now need 8 amplitudes, or 2 to the 3. And what this is saying is that as I increase the number of quantum bits, I need exponentially more information to describe the quantum state, which sort of hints at why quantum computing is different than classical computing. Okay, so this establishes sort of our abstract representation of quantum information. Now let's talk about how we actually manipulate this information. So it is true that in quantum computing, we really just do like to put classical computing terms and add the word quantum in front of it. And so in quantum computing, we write down quantum logic gates. Now, in a single qubit, these logic gates have a really nice visual representation. So here, for example, I've written a Y gate. And what this gate is telling me to do is to take the state of the system on the block sphere and rotate it 180 degrees about the y-axis. Now, I could write other gates like this. For example, x is a 180-degree rotation about the x-axis, and you can imagine what z is. And I can also write other gates like y/2, which is a 90-degree rotation instead of a 180-degree rotation. And generally, these single qubit gates are responsible for turning classical-looking states like 0 or 1 into superposition states like 0 plus 1. We also have 2 qubit gates, and these are generally responsible for creating entanglement between qubits. So for example, the controlled NOT gate flips the state of one qubit conditional on the state of the other. And we also have a gate that has a funny name, the square root of swap. And what this does is it basically exchanges half of the state of one qubit with half of the other. And so in that way, you can sort of shuttle half the information to the other qubit, which entangles the two of them. Okay, so with that, we actually have all the ingredients we need for our model of quantum computing. For a physical representation, we need some sort of quantum system or particle that has 2 discrete states. Our abstract representation is to write down 0 or 1 for each of these states and combine them using complex amplitudes, where each of these amplitudes, if you square them, gives you the probability of measuring this particular state. To manipulate that information, we write down a quantum logic circuit, which is a combination of quantum logic gates. The single qubit gates are generally responsible for creating superpositions, and the 2 qubit gates are generally responsible for creating entanglement between qubits. And finally, at the end of the day, what you get out of running this quantum logic circuit is a probability distribution over all the classical possibilities. And when you go to measure the quantum computer, what you're going to get out is one of these classical possibilities according to this distribution. Now, often what we're actually interested in is not a single bit string, but actually what this distribution is. And what we'll do is we'll prepare the initial state, run the quantum logic circuit many, many times, and get a sample of this probability distribution, or we call this process sampling the bit strings of this logic circuit. And this is important because this is plays into exactly what the beyond classical task is towards the end of the talk. Okay, so this is a sort of very simplified but complete picture of quantum computing, but I haven't explained exactly yet why quantum computers might be powerful. So to get at that, let me give you another view of a quantum computer, instead now as an interferometer. So when we perform a quantum computation, we prepare some initial state, for example, both of the qubits here in the 0 state. We then apply these logic gates, and each one of these logic gates expresses some sort of transformation of this initial state to one or more other states. And so we keep doing these transformations. And because the states themselves can be complex, these paths between the states can also be complex. And what that means is that while we're doing this computation, interference is happening between the various states. So for example, here I've sort of tried to express positive paths as red and negative paths as blue, perhaps. And they can constructively and destructively interfere with each other, these paths. And at the end of the day, what you're going to get is some sort of probability distribution that expresses all of the different paths that could have arrived from the initial state to the final state, considering all the interference effects that have happened. So when you're designing a quantum algorithm that's supposed to solve some problem, ultimately, a lot of the time what you're trying to do is you're trying to design it so that it'll amplify the correct answer that is the solution to your problem. And the reason that classical computers have a hard time keeping up is that these interference effects are occurring in this sort of exponentially large space in the number of qubits that I was explaining before. And so this is just a lot for the classical computer to keep track of. Okay, so that was my lightning introduction to quantum computing. I can stop now and take any questions that people might have.
I'll drop a question, like in case someone may also have this kind of question. So can you go back to the slide about 2-qubit gates?
Mm-hmm.
And could you explain more like how entanglement is generated from the 2-qubit gates? Yeah,
that's a good question. So let's, I'll show maybe a little bit of an example later on, but we can just go through an example. For example, if the controlled knot, if I prepare one of the qubits in a superposition position of 0 and 1, and I use this as the control part of the gate, then that says to the other qubit, you should flip to the, you should do a flip, but you should sort of do a flip if I'm 0 and not a flip, or you should do a flip if I'm 1 and not a flip if I'm 0, but I'm in both of them at the same time. And ultimately what you'll get out at the end is either this qubit is 0 and this qubit is flipped, or this qubit is 1, sorry, the other way around. This qubit is 0 and this qubit has not flipped, or this qubit is 1 and this qubit has in fact flipped. And so, sorry, that wasn't a very good explanation, but that is one example of how you get entanglement out of these gates.
So can I understand it like in this control scenario, we should be getting like kind of like an if statement, but instead we get two qubits.
Yeah, that's right. You can think of this as a conditional statement, but the thing that's controlling the condition can be in a superposition of true or false. And so the answer you get at the end is a superposition of false and I didn't do the thing, or true and I did do the thing, and that's how you get entanglement.
Thank you. And there are two other questions. The first in the chat. The first one is, could you repeat why classical computers struggle?
Yeah, so imagine I have 10 qubits, 2 to the 10 is 1024. And so to simulate sort of what's going on in this classical computer, I have to understand all the possible ways this initial state might map onto 1024 final states while considering all the possible different paths that are happening in these quantum logic gates. And this problem sort of blows up eventually once you get to, say, 50 qubits, which is the scale of problem that I'll be talking about today. So to the 50, for example, is 9 quadrillion, I think is the number. And so you have to just sort of keep track of all the different ways that the quantum logic gates are mapping this initial state onto the 9 quadrillion possible answers at the end.
And there is another question. Could you explain more why the problem Google solved is hard classically?
Yeah, I think I answered that a little bit just now. Basically, the state space is very large, and keeping track of all the things that are going on here is just a lot of things for the classical computers to compute. I will say that trying to understand why a quantum computer is more powerful than the classical computer is actually not as easy as people make it out to be. I explained that this exponentially large space is important, but that's actually not the only reason, and interference, it turns out, is also really important. And the reasons there are kind of subtle. So yeah.
Cool.
Okay, great. Okay, so hopefully that was, you got something out of that lightning introduction to quantum computing. And now I'll move on to sort of what Google's approach is to trying to build one of these devices. So I've already explained to you that you can use electrons, for example, to try to represent the two states 0 and 1 in a quantum computer. But electrons are really small, right? And trying to work with these really small objects is going to be really hard. Moving up in size scale, you could try to use atoms, for example, to do quantum computation. And in fact, people do this. In fact, Duke is one of the powerhouses in using atoms or ions, to be more specific, to do quantum computation. At Google, though, we build what we like to call artificial atoms. And these are electrical circuits that are supposed to sort of mimic the quantum properties of atoms. In particular, these are circuits that are made of superconducting materials. And a superconductor is a material that has two important properties. The first is that it tends to zero resistance when you get really cold, and that helps these circuits preserve their quantum properties. And the second is that superconductors, in a superconductor, all the electrons in the circuit will condense down into the same ground state, which means that the circuit, which nominally has at least trillions of atoms and electrons, will ultimately behave as if it has one quantum degree of freedom. Okay, so nature gives us perfectly good atoms. Why go and build our own? Well, there's a number of advantages to building these artificial atoms, and they have to do, and one of them has to do with the fact that these superconducting circuits are actually just really big. So in this example, the circuit here is about 0.5 millimeter across, which means that if you squint, you can actually see it with your naked eye. And the fact that it's big actually means that it's easier to control. For example, here I've got a bunch of wires that are going up right next to this circuit. And you can try to imagine running a wire up next to an atom runs you into a paradox of, well, doesn't the wire have to be made of atoms as well? The second thing is that while nature gives us atoms, those atoms sort of have fixed properties. And when we build these qubits ourselves, we can actually engineer them to have the properties that we want, which can be convenient for designing them to operate in very specific ways. And finally, the way we build these superconducting qubits is similar to how computer chips are built. And this gives us hope that we can leverage techniques that have already been used in the computing industry to try to scale up these devices. So let me tell you a little bit more about the specific qubit that we build at Google. It's called a Transmog Qubit, which was developed by a group at Yale in the 2000s. The qubits we build are made of aluminum on silicon, and the two important components here are a capacitor, which is formed by this cross shape here, where the other sort of paddle of the capacitor is this ground plane, and a device known as a Josephson junction, which is a special superconducting device, but its function here is really as a nonlinear inductor. So if you put an inductor and a capacitor together, you get an LC oscillator, and it's a nonlinear inductor, so we have a nonlinear oscillator. Oscillator just means it responds to a very specific frequency. In our case, usually typically about 6 gigahertz. And nonlinear means if I put energy into the system, its properties actually change, which is important for getting it to behave like an atom as opposed to a classical circuit. Now, a good analogy for the transmog is actually a pendulum, which is also a nonlinear oscillator. And you can sort of think of the motion of the pendulum as very roughly corresponding to how the charges slosh around in the transmog. And the ground state of the transmog, or the zero state, is the charges being sort of mostly at rest. And the one state of the transmog corresponds to the charges sort of in motion or sloshing around. But just remember that this pendulum is oscillating at about 6 gigahertz. So we have a variety of ways of how we control these transmog qubits. Coming in from the right here is a drive line, which is responsible for doing single qubit gates. And so what we do is we actually shoot resonant microwaves at this transmog to get it to do what we want. I explained earlier that single qubit gates can be thought of as rotations about on the Bloch sphere. And the area of these pulses that we shoot determine sort of the rotation angle or how much it rotates. And the frequency and phase of these microwave pulses determines the rotation axis, for example, the difference between x and y. On the subject of shooting microwaves at our qubits, that's actually how we do the readout or the measurement of the state of these devices. So coming in from the top here is something called a readout resonator. This is a linear oscillator, which is coupled to our nonlinear qubit. And what we do is we shoot microwaves at this linear oscillator, and then we look at the signal coming out. And depending on the state of the qubit, this oscillator actually has a very slightly different frequency. And we can see this difference in frequency and differences in the signal that we read out at the other end with a detector. So on the right here, I'm showing what this experiment sort of looks like. Each of these dots corresponds to sending a microwave pulse at this oscillator and looking at the response, where blue is where we prepared the qubit in the 0 state, and red is where we could prepare the qubit in the 1 state. And you can see that we can very well distinguish between the 2 states by looking at the scattered signal here. Now, in order to do quantum computation, we need to be able to entangle our qubits or couple our qubits together. And one very simple way to do this with superconducting qubits is to just literally just put them right next to each other. And this forms what's called a capacitive coupling between the 2 qubits. And the mechanical analogy for the system is 2 pendula. Each of these pendula, remember, is like one of the transmons that are coupled together with a spring. So I actually have a short video here to demonstrate what happens. Setup for the video is that one of the pendula is going to be held at rest, and the other one starts off in motion. And what you can see here is that which pendulum is swinging and which pendulum is at rest actually switches over time. And so it's this behavior that we actually exploit to do entanglement. So we call this behavior swapping. I alluded to this earlier with the square root of swap in the entangling gates. But what we don't want is for this swapping of information to happen between the 2 qubits all the time, because that means we would basically have no control over each individual qubit. So coming in from the bottom here, we have these lines which their purpose is to tune the frequency of the qubits, which we can do because again, we can sort of engineer the properties of these qubits. And what we do is we can tune the qubits in and out of resonance. It's when they're on resonance, when they have the same frequency, that the swapping occurs. And so for example, we can start with the qubits very far apart in frequency space, put them on resonance with each other for a very certain amount of time, and that causes all the information to swap, for example, from the left qubit to the right qubit. So that is like a transformation that corresponds to going from 1, 0 to 0, 1, which we call a full swap. On the other hand, if we let this process occur for only half that amount of time, we do the square root of swap that I talked about earlier. So we turn 1, 0 into a superposition of 1, 0 plus 0, 1. And for those of you who know a little bit about quantum computing, this is a Bell state, which is sort of a hallmark or a very fundamental state that shows entanglement. Okay, so these are all the basic ingredients that make up our qubits. We have a nonlinear oscillator that's called a Transmog Qubit. We have a line coming in from the right that does sort of single qubit drives, which do our single qubit gates. We have this thing, a linear oscillator coupled at the top, which allows us to read out the state of the qubit. And from the bottom, we have these frequency controls. And when we put the qubits together, these allow us to do entanglement gates. So now I want to talk about why making these qubits is actually a fairly difficult task. I explained earlier that these transmog qubits are in fact, composed of many, many atoms, and all these individual parts, for the atoms all the way up to these wires, have to work together to behave as one quantum object. Now, while the wires allow us to control the qubits, they also bring in the influence of the environment, which can be detrimental to the operation of the quantum system. And so the story of trying to make these qubits, to engineer them, is the tension between isolation versus control. And this is true of any other quantum system as well, including trapped ions and other kinds of platforms. And so in the next few slides, I want to tell you about the sort of different engineering efforts we go through to try to make these qubits work. It starts at the sort of microscopic level when we go to fabricate these devices. We spend a lot of time thinking about material science to actually make sure all the surfaces in our circuits are clean, because even sort of atomic defects in these qubits can lead to degradation of the quantum properties of our devices. Going up a little bit in length scale, we actually also do a lot of specialized microfabrication to be able to route wires on our devices, for example, without damaging the qubits. Once we've actually made the qubits, then we need to be able to get them to talk to the outside world. This is a whole sort of field called packaging. So on the left here, you can see a completed qubit chip is wired up to a superconducting printed circuit board, which is then encased in this sort of larger enclosure here, which has 2 purposes. The first is, as I alluded to, connecting the qubit to connectors here, which then go to wires to the outside world. which allow us to actually do the control. And the second thing is to actually shield the qubit from the influence of environmental effects. So for example, from infrared radiation or even the Earth's magnetic field could be detrimental to these devices. And once you package up a device, the next thing it has to do is go through sort of the final stage of isolation. So when we package them, we put them into a machine called a dilution refrigerator. And this is a device that at the bottom of the plate here, it gets down to a temperature of 20 millikelvin, which is 100 times colder than space. Inside this dilution refrigerator, when it's cold, it's also under extremely high vacuum. And these are sort of all the lengths we go to ensure that our qubits have a really quiet environment in which we can operate them. And so in our lab in Santa Barbara, we sort of do engineering order, not over 9 orders of magnitude, from nanometers all the way up to meters for these dilution refrigerators. At some point, we'll probably have to engineer entire buildings around these devices to be able to house them. So, look forward to that in the future. But with that, let me tell you a little bit about 2 of the devices that we've made in our lab, which sort of illustrate the story of trying to control these devices. So the first really big device that we made in our lab maybe 3 years ago was a device called Bristlecone. This is a quantum processor that had 72 qubits and 144 control knobs, 2 for each of the qubits. And this is where we really learned a lot about making these devices as well as controlling them. But the device I'm going to tell you mostly about today is a device called Sycamore. This is a device that has 53 qubits, which might sound less than 72 on the Bristlecone device. But in fact, it has even more control knobs at 196. And the reason for these increased control knobs is, I explained earlier that when we couple the two qubits together, it's like having a spring that ties together the 2 pendula. And what we've added here is a way to control the tensions of these springs. So we can actually turn the coupling between the qubits on and off at will, which gives us both increased control and isolation over the qubits. And I think the main message I'm trying to get across here is that just having more qubits doesn't equal more computational power. You need both a lot of qubits as well as a lot of control over them, which is what we've achieved in the Sycamore device. Okay, so that tells you a little bit about how we've built the devices. Next, I want to tell you a little bit about actually how we program these devices. So I showed you earlier these quantum logic circuits, which consist of single qubit gates, which do superpositions, and 2 qubit gates, which are responsible for entanglement. And when I see one of these quantum logic circuits, I'm sort of an amateur musician in my other life, and this reminds me a lot of a musical score. Each one of these lines is some roll corresponding to one of these qubits, and we read these logic circuits from left to right, just like in a musical score. Now, in order to actually play the music of quantum computing, we need instruments. And so for that, we build our own custom instruments in Santa Barbara. And instead of putting out sound waves, these instruments put out electrical waves. They're built to be high speed and high precision so that they have really fine control and really fast control over our qubits. And on the right here, you can see actually sort of the scale of how many wires we need and how many instruments we need to be able to control our Sycamore processor. Now, with our instruments, we need to move on to actually learning to play music. And just to extend this analogy a little bit further, if I see a note in a musical score, that's an instruction to play an instrument in a certain way. And at the end of the day, what the instrument is supposed to do is produce a sound wave, which has a certain frequency, amplitude, and shape. And this is exactly the case in quantum computing as well. When I see a quantum logic gate, that is an instruction for our control instruments to play an electrical wave which has a certain frequency, amplitude, and shape. And in the musical case, if I get any of those properties wrong, I have made a mistake in my note, right? And in the quantum case, if I make a mistake in the frequency, amplitude, or shape of these electrical waves, I'll do a slightly wrong quantum gate, which leads to errors. And so the process of learning how exactly the correspondence between our quantum gates and the electrical waves we need at the end is a process called calibration. And this is very near and dear to my heart because this is what I personally work on with Google. And we like to represent calibration, or the process of learning how to execute quantum logic using a graph-like structure, which I've shown here. Each one of these circles here, or nodes, represents basically a physics experiment to try to learn something about our system. And each of these arrows represents a dependency, which says, in order to learn this thing, you need to know about this previous thing. Starting at the left, we basically know nothing about our system. And ending up at the right, we've hopefully learned enough to be able to execute quantum gates with very high fidelity. And this is just an example graph for calibrating 2 qubits for the 53 qubits in Sycamore. You can imagine that required thousands of nodes or thousands of physics experiments that we had to do. And just to give you a sense of scale for sort of the complexity of this problem, these two circles right here, coming up with these two physics experiments was a sizable chunk of doing my PhD. And so you can imagine how much information we've really distilled down into these calibration graphs in order to tackle the problem of learning how to execute quantum logic and doing quantum computations on Sycamore, with high fidelity. So what has all of this gotten us? Well, here is a heat map of the performance of the Sycamore device. Each one of these crosses represents a transmog, and it's the fidelity of a single qubit gate. Each one of these squares represents the coupling between 2 qubits, and it's the color is the fidelity of the 2 qubit entanglement gates. And we've done a number of achievements on the Sycamore device. We've achieved really low error rates in both the single and 2 qubit gates. But maybe more importantly, we've done this with really high efficiency. We can execute a lot of these two qubit gates in parallel, which is something that a lot of other systems can't do with high fidelity. And we also have a fairly high connectivity here, where each of these qubits is coupled to typically 4 of its neighbors, which allows us to execute a lot of entanglement gates at once. Okay, so that is a summary of all the stuff we do at Google to try to build and calibrate these quantum processors. I'll stop again for questions if people have them. All right, if there are no questions, I can move on to the next section then, which is to try to define what is the sort of beyond classical task that we're trying to do here. So I want to turn again to a classical analogy.
Sorry, Jimmy, I think there's a question.
Yeah, go for
it. You can just ask, you can unmute yourself.
So yeah, thank you for allowing me this great opportunity. It's an honor for me. My question is, it's not related to specifically the section you've mentioned, but it is more general.
Mm-hmm.
So the question is, if demonstrating quantum supremacy is a milestone we've just achieved recently, do you think the research implemented for finding useful applications for quantum computing, like quantum machine learning, is overhyped and that it is basically ahead of its time?
Good question. So I think there is certainly a lot of hype in quantum computing, and I think we've gotten a little bit better about managing expectations. I would say there is not a sort of killer app yet for these near-term quantum devices, which still have very high error rates. We've not found something definitive that says, oh, this will be a thing that can beat a classical computer at a useful problem. And I'll talk a little bit later about this, but one thing we're really working on is error correction to try to reduce the error rates. And we think we're on sort of a 10-year timeline to try to build an error-corrected quantum computer, which we think will actually do something useful. And what happens in the interim is still a bit of a mystery, but I'll get to that maybe a little bit later. Okay, cool. So let's move on to talking.
Sorry, there's another question in the chat. What do people in the quantum group at Google do to prepare for this type of groundbreaking work?
Like, what kind of education did we have? Is that the question?
I don't know, but I think Nagak, you can just unmute yourself and ask.
Yeah, so not just education, but also just like what kinds of research do they do before they enter the group?
Okay, yeah, I can talk about this in, or I can talk about this now, but I did my PhD in a group that did very similar work. In fact, it was the group that actually ended up joining Google. So in a way, it's a sort of continuation of my PhD. Generally, people who go into the field, at least in physics, do their PhD in some sort of work related to quantum computing. But probably the most important thing is to have, to be able to do a PhD, the most important thing would be to have some sort of research experience in a lab that does experimental physics. Now, there are a lot of other things that people do that aren't just physics. I talked a lot about engineering. And so microwave engineering, for example, is a big thing, as well as we do a lot of just software engineering as well, computer science kinds of things. But I can talk a little bit more about that after the talk, maybe. Okay, so I want to start with a classical analogy for the sort of task we're trying to do. Imagine that it's not COVID-19 and that I can give you this talk at Duke University and somebody wants to play a game with you, which involves a game of directions. They're going to give you a starting location, and then they're going to give you a sequence of directions that you're supposed to follow. And the directions might look something like walk 100 feet, turn 47 degrees, walk another 200 feet, et cetera, et cetera. And to make sure that this game is unbiased and that you can't cheat, they're going to draw the directions from a hat so that they're random. And they don't, and you don't know ahead of time what the directions are going to be. They're going to give you a GPS reader, and you're going to follow the directions. And at the end of the day, you're supposed to write down what you got on your GPS reader. And your friend has the benefit of using a Google Maps, for example, to compute exactly where you should have been, the expected coordinates. And they're going to score you on how close your GPS reading is to the expected coordinates. Now, you pass this test with flying colors, but your friend says, oh, let's turn this game now into a quantum game. So in the quantum world, we're still going to have starting coordinates, but now these are going to be sort of the states on block series of qubits. We're going to give you directions that are going to come in the form of a quantum logical circuit, which again might follow a pattern like alternate single and 2 qubit gates. And again, to prevent cheating, it's going to be a random quantum logical circuit where the gates are sort of drawn from a hat. And the final coordinates are going to be the probability distribution over all the bit strings of the system. And again, your friend has the benefit of using a classical computer to simulate this process, and they know what this probability distribution should be. And in the quantum world, we like to call this sort of score of closeness the fidelity. Now, the sort of connection between the quantum game and the classical game is something I alluded to earlier, which is that when you write down a quantum logical circuit, it's sort of describing paths to go from the initial state to the final states. But remember, these paths have all these interference effects, and as we increase the number of qubits, the sort of state space that we're talking about is no longer two-dimensional, as in a single qubit or the real world, but potentially the dimension of the state space is in the trillions or quadrillions. And so, as you increase the number of qubits, you're going to have a hard time trying to compute what's going on, but so is the classical computer. Just to give you a sense of what the output distribution at the end of this game is supposed to look like, I've done a little bit of simulation here. So here is a simulated distribution for running a random quantum logical circuit on 12 qubits, where the x-axis here is all the possible classical bit strings, so 12 zeros all the way up to 12 ones in order, and the y-axis is a normalized probability. So when you look at this, this distribution is entirely random, which makes sense because the logical circuit in the beginning was random. But the important thing here is that some of these points are much more likely than the others. And a good analogy here is the phenomenon of laser speckle. So if I shine a coherent laser through a rough medium, or if I bounce it off a rough surface, I'm going to get certain points of light here that are more likely than others. And what happened here is really due to the details of that rough surface. And so in the same way, some of these bit strings are much more likely than others. I explained earlier that when you try to create quantum algorithms, you're trying to amplify certain correct answers. But if I write down a random quantum algorithm, I'm going to get randomly certain answers that are amplified. And which of these bit strings are more likely depends on the exact nature of the random quantum circuit that we ran. And so you can think of these likely bit strings as sort of a fingerprint for the quantum circuit. But we were only going to get these likely bit strings if we actually execute the correct thing. And so that's sort of the game here. We want to see that a quantum computer can mimic this distribution very well with low error. Okay, so as we try to tackle this problem, and as we scale up to the 53 qubits that we have in the Sycamore device, we sort of run up against two logistical challenges. The first is that we want a classical computer to be actually checking the fidelity of the Sycamore device. But as we get to 53, and the first thing is that trying to estimate this fidelity with 53 qubits or over 9 quadrillion possible bit strings is actually a really hard statistical problem. And the second thing is that we're trying to claim that we can beat classical computers, but if you need a classical computer to check that your quantum computer worked in the first place, how can you possibly claim that you've actually done something that's beyond classical? So I'm not really going to address number one here, but due to time. If they're interested, there's a whole, it's really interesting actually how we do this, and it's described in the paper. But I will talk a little bit about point number two here. And the key is to do extrapolation. So what we're going to do is we're going to find logical circuits where we can vary the computational difficulty of them. And we're going to start with the easy circuits, and Sycamore can probably execute these with high fidelity. And as we increase the computational difficulty, for example, by adding more and more qubits, the computational difficulty is going to go up, but Sycamore's performance on this problem is actually also probably going to go down, just because there's more ways for things to go wrong. But eventually, as we add more and more qubits, it'll eventually enter a regime where the classical computer can no longer actually do this computation. And what we hope to see is that as we follow this curve, that Sycamore is on track to achieve computation in this regime with non-zero fidelity. In other words, they can execute the computation at least some of the time without error. Okay, so to summarize the task at hand, what we're trying to do here is sample bit strings from randomly generated quantum circuits and achieve non-zero fidelity. On a quantum computer, we can sort of just natively run these circuits on our quantum processor. And on a classical computer, we have to sort of simulate the entire process, which becomes exponentially hard. We run this task in two regimes, a classically tractable regime, where we hope the quantum processing time is short, but the classical processing time is long. And as we scale up the complexity, eventually we reach an intractable regime where the quantum processing time is short and the classical processing time is practically unachievable. Okay, in the interest of time, I'm just going to keep going with the last section here to show you how we actually achieve this task. So first, let me tell you a little bit about the actual circuits that we ran. So the circuits that we ran had take this format where we alternate between single qubit gates and 2 qubit gates, which sort of tile around the grid in a fixed pattern. And we alternate these in what we call cycles, of where one cycle consists of a layer of single qubit gates and a layer of 2 qubit gates. And the randomness of these circuits actually comes in the choice of these single qubit gates. So we randomly draw these single qubit gates from a hat, and for every circuit that we run, and that creates sort of the randomness in our logical circuit. Now, what we need is a way to be able to vary the computational complexity of these circuits, and we have a number of ways of doing that. The first is by varying the size of the circuit, either in the number of qubits or the number of cycles that we run. If we want to keep a fixed size, one thing we can do is actually reduce the number of entanglement gates in a very specific part of spatial location on the circuit. And what this does is actually reduce the amount of entanglement that happens between the left part of the chip and the right part of the chip, which makes it substantially easier for classical computers to simulate. And we call the difference between these circuits reduced versus full circuits. And finally, if we want to keep the same gate count in our circuits, we can actually change the pattern which these 2 qubit gates tile around in. And one of these patterns turns out to be easy and one of them turns out to be hard. So we call them easy circuits and hard circuits. So I'm going to focus first on these easy circuits because they are still classically computable. And before I give you the results, though, I want to give you a prediction for how well the Sycamore device should perform on this task. So earlier, I showed you this heat map of all the fidelities of the components of these gates inside these quantum logical circuits. And when we put together these logical circuits, if we want to predict what the fidelity of the whole circuit is going to be, we can simply just multiply the probability of not getting error from each one of these individual gates. And so this black line is essentially that multiplicative model, where as we increase the number of qubits, the fidelity sort of goes down because we're adding more and more places where an error can happen. And now if we look at the data for the fidelity of the actual execution. We can see that it matches really well with this prediction. So the red circles here are the full versions of the easy circuits, and green X's are the reduced versions of the easy circuits. And what we see is that the full circuit and the reduced circuit match each other really well, and they both match the prediction really well. And this is pretty remarkable because when we made these predictions, we're using error rates that are derived from the gates themselves, which sort of operate in a computational space of up to 4. But the entire computation executes on this computational space of 9 quadrillion. So the simple error model that just takes into account the errors of the gates apparently works over sort of 15 orders of magnitude, which is pretty remarkable here. So now that we're confident that the full circuits and the reduced circuits are essentially equivalent in terms of fidelity, we can move on to the hard circuits. So now with the hard circuits, we can only run the simplified or reduced versions because the full versions are too hard to classically simulate. And here what we're doing is we're keeping a fixed number of qubits and adding more and more cycles to the circuit. And when we get to 20 cycles, we get a fidelity of about 0.2%, which might not sound like a lot, but it's still appreciably bigger than 0. And this is the point of, this is sort of the computational point that we'll be comparing to classical computations. So our classical computation here are 3 different supercomputers that we ran with our collaborators. One's in Europe, in Germany, with the Jülich Supercomputing Center. We also worked with NASA, as well as sort of the most powerful classical computer in the world, the Summit machine at Oak Ridge National Laboratory. Now, there are 2 different algorithms that we compared to on classical computers. I don't have time to get into it exactly what they were, but one of them is called, this is something I would call the Schrodinger algorithm. This is actually fairly fast in terms of time. In order to do the same computation that we did for the hard circuits, it would only take about a day or 2 to actually do this computation. But the caveat here is that the amount of memory that you need to sort of store that entire computation was about 65 petabytes, which exceeds the amount of RAM that even Summit has. So that was not a viable path on the Summit machine. On the right is a different algorithm, which is more memory sort of efficient. But the trade-off there is that in order to do the entire computation, we estimate that it would take 10,000 years, even allowing for 0.1% accuracy, just like the quantum computer. So to summarize, what we've done here is that we've shown that Sycamore can run these random logical circuits on 53 qubits with sort of non-zero fidelity, up to 20 cycles. The fidelity that we achieved here is well predicted by a simple model that just takes into account the individual errors on the gates themselves. And achieving the same fidelity on the same size circuits on a classical machine requires exponential resources, which even a year after we did this experiment, no one has actually been able to marshal in order to try to match the computation that we did. Okay, so in the sort of closing moments, I just want to give you some perspective on what we've done here. In sort of the big picture, we've shown from a computer science perspective that a quantum computer works sort of fundamentally differently than a classical computer. There is a sense in which an abacus and a modern computer are similar because you can simulate one versus with the other with sort of polynomial overhead. But evidently, this device that we've built in Santa Barbara requires exponential overhead to simulate. And that challenges something called the extended Church-Turing thesis. From a physics perspective, we showed that quantum mechanics still works in these very highly entangled systems, and that quantum computing is still possible, even after a scale of 53 qubits. From our perspective, though, here at the Google sort of quantum hardware team, we put a lot of engineering effort, as I explained, into building the Sycamore device. And doing this beyond classical task is really a sort of an integrated systems test of the whole thing, and we think it passed with sort of flying colors. Okay, so what's next in the field of quantum computing? What I have here is sort of a phase diagram of possible quantum computers, where the x-axis is the number of qubits and the y-axis is the limiting error rates on the operations. With Sycamore, we've sort of inched out into the classically intractable regime, but what we did is sort of not anything that people would generally consider to be useful. And what people are looking for now are possible near-term applications for devices like the Sycamore device, which have appreciable number of qubits, but fairly high error rates. But another place we're going is to try to do error correction, which I'll explain in a second. So in terms of near-term applications, this is something we're interested in as well. We recently published a paper using, I think, 10 qubits on a Sycamore device to do a chemical computation. Or for example, sorry, this is 12 qubits, and we actually computed the binding energy of a a hydrogen chain with 12 hydrogens in it. And so quantum chemistry is something that's very popular right now as a potential application of these near-term devices. But a lot of what we're also working on is error correction. You know, we got this, we did this beyond classical task, but we only got the answer right 2 out of 1,000 times. And getting to reduced error rates is going to require error correction, which the basic idea behind that is to combine a bunch of these single physical qubits into one bigger logical qubit. And one way to do that is using something called the surface code. And in fact, we built the Sycamore device with the surface code in mind. And so we're continuing research into reducing the fundamental physical error rates in these devices, as well as figuring out how well it works when we put these qubits together to try to form logical qubits with lower error rates. Sort of the effort to build an error-corrected logical computer, that's going to eventually require millions of qubits to do something useful, we think. And we sort of have a 10-year timeline with which we think this can happen. So, 2019 is when we did this beyond the classical task. We hope to hit 1,000 logical qubits in, say, 3 to 5 years. And hopefully in 10 years, we have this million-qubit error-corrected quantum computer, which might do something interesting at that time. All right, so with that, I'd like to thank you all for paying attention to this virtual talk. I'd like to also thank everybody on the team at Google, in the quantum team, who contributed to this work. I'm just really a small cog in this whole machine. And finally, I'd like to thank Nora and the rest of DuQIS for organizing this whole talk.
So I guess, do you guys have any questions? Well, actually, I have one. Can you, so are all the qubits in a 2-dimensional like arrangement, or do you stack them together into a 3-dimensional? Because we're building, like you said that Google is going to build to 10 to the 4th number of qubits or more. Mm-hmm. So how are you going to like lay them in a two-dimensional space?
Yeah, that's a good question. So our plan right now is to continue on doing 2D, because going to the 3rd dimension is quite challenging in terms of how you would actually try to build that. One thing that you might have noticed here is that what we're hoping to do is build, say, 1,000 qubits into one chip maybe, or a module, and then put these modules together and to maybe try to get to these larger numbers, because putting 1 million qubits on a single chip is just going to be really hard. But exactly how these modules and connections are going to work is still a research question.
So another like question just follow from that, like if we are having a really large kind of like a chip, so how can 2 qubits at like far away from each other can have entanglement, like can have pretty good entanglement, or entanglement only like lives locally?
That's right. So the only entanglement gates we do are between the neighbors, but that's sort of one of the advantages of doing the surface code actually is that you only need these nearest neighbor connections to do error correction. And then once you get the error rates low enough, hopefully you can do the computation you need with low enough error rates. And that might, for example, involve the logical qubits doing swapping operations to be able to entangle with each other over long distances. But yeah, that generally requires chaining entanglement gates together.
Okay. There's another question in the chat. You can ask.
Yeah, okay. I'll let Mustafa go.
Okay, thank you for allowing me to ask first. I've been wondering whether Google offers remote internships for international students.
That's a good question. I think international is going to be tough next year, and I don't remember what the reason is, but we do offer remote internships. Yeah, but I think I have to remember why, but for some reason it has to be in the US for next year.
Yeah, I had a couple of questions actually. The first one was around so currently with the Sycamore system, which as you said 53 qubits,
Mhm.
in terms of applications using, say you're using a surface code as your error correction protocol, how many qubits at most can be used for like a near-term application? I know you spoke about a 10 qubit example for a was it a chemical simulation? But
That's right.
at like the limit of the number of qubits that can be used using the surface code protocol, or can you go more than that as of now?
Good question. So let me clarify. This chemistry application that we showed here doesn't use error correction at all. There are some sort of like error mitigation techniques, which involve trying to find symmetries, for example, that the system should obey, that you can get rid of data that doesn't follow that symmetry, for example. To build even the smallest logical qubit requires 17 qubits, and to build any sort of practical logical qubit that has reduced error rates will take at least the entire Sycamore device to build sort of one logical qubit. Yeah, these sort of more near-term applications are not going to be using error correction in the way I've discussed it here, and will instead just try to sort of natively use the qubits by themselves.
Oh, okay. So potentially the entire Sycamore chip can be just one logical qubit under a surface code.
That's right. Yeah. Eventually, a single surface logical qubit will probably require 1,000 physical qubits, for example.
Okay. Yeah. I think my next question was in terms of, you said you spoke a lot about optimality and processing. I was wondering how much of this also is software driven. For example, just bouncing off of the question Nora asked. So if you want to perform an entanglement or a simple CNOT between two qubits which are very far away, there are a lot of swaps which you'll have to do. So is there some sort of optimality routine that is run using software on the algorithm itself before it's executed on the chip?
Yeah, that's right. So there are two different regimes to answer your question. The first is in sort of near-term devices. People do spend a lot of time figuring out, people have written down these logical circuits that are in textbooks, for example, and you want to execute them on a real hardware. What is the best way to transpile or compile them onto what is actually available on the hardware? And that is a really big focus right now. There's also in the other regime of, once you have an error-corrected quantum computer, what is the most efficient way to go about doing the computation union? And that's also a very large part of the research, and many people at Google work on that, for example. So yeah, there is a lot of room for sort of software optimization before you actually go execute on the quantum computer.
Perfect, thanks. And then just lastly, not related exactly to what you spoke about, but more around, so going forward, do you expect to have like potential full-time roles for graduate students in like the upcoming year in both the hardware and the software side of the effort?
That's a good question. So we are definitely hiring right now next year for full-time roles. Being a student at the same time is a little bit tricky, if that's what you're asking.
No, like for a student who's expected to graduate soon.
Oh yeah, for sure. We're definitely hiring next year.
Thanks a lot.
Yep.
There's a question in the chat. Why does a heat map have a triangular region at the top that is empty?
Oh, okay. So you might have caught this, but Sycamore was supposed to have 54 qubits, not 53. It happened that this one broke in a way that we couldn't control it. So.
I have a, sorry, go ahead.
Oh. Hi, Jerry. Can I ask two questions, actually?
Yep.
So my first one is that during the supremacy experiment, like how do you guys, you mentioned that there were easier circuits and harder circuits. Mm-hmm. And obviously that probably depends on like the number of qubits and like the circuit depth and all of that. And I was wondering like how you guys, is there anything that you did to like ensure that the circuit depth doesn't exceed like the decoherence time, or like is there any way that you compensated for the coherent and incoherent errors in the system like throughout your experiment?
Yeah, that's a good question. We didn't do any error mitigation that I think you were trying to allude to. And in fact, I mean, you can see the decoherence, right, when the fidelity goes down with the number of cycles. And if we had gone any further, probably, then the signal probably would have been lost.
Okay. So as you were mentioning you were mentioning about like you guys are working on error correction and stuff. So I was wondering, like, once you guys have more qubits and like you can demonstrate error correction or whatever, would you guys kind of do like repeat the same supremacy experiment with the fault tolerant system or like the error corrected system in the future?
Yeah, that's a good question. So quantum supremacy with error-corrected logical qubits is something that we have looked into. I think this is more on the scale of tens of thousands or hundreds of thousands of qubits. So we're not anywhere close to that yet.
Okay, thank you.
I have another question, like on this exact slide or the slide before that. So the reduced circuit, is it safe to assume that the reduced circuit's fidelity is the same as the full circuit when it goes to high dimension space?
Yeah, that's a good question. So the reason we actually had to run both circuits is to just experimentally make sure that they would give the same fidelity. But for example, here is the 53 qubit circuit where the full circuit and the reduced circuit gave very similar fidelities. So we trusted from this data that they would be relatively close, even with the hard circuits, for example.
Cool. And for your calibration PhD thesis, you mentioned that your PhD is only a little part of the entire picture. I'm just curious, like, why this is the case? Like, shouldn't the calibration and like a unit thing, like general thing?
I guess I can clarify a little more. So like each one of these things is a physics experiment, right? So I don't know if you guys are familiar with like Brawley flopping, but Brawley flopping is somewhere early on here. My specific thing was figuring out a way to figure out what are the parameters in the single qubit pulses, how to measure it better. That wasn't the only thing I did for my PhD, but you know, it was a decent chunk of it. But I would say there's multiple people's PhDs baked into this whole graph. So.
Hi, so after you guys announced your quantum supremacy, I think IBM came out and said that like they think it would have taken slightly less time to classically simulate it. Were they just being petty, or like yeah, like what did you think?
I'm not going to make any value judgments about it, but I will explain what they were talking about. So I mentioned it here that there's two different algorithms you could do. To get into a little bit more detail, the Schrodinger algorithm, which we called it, is to just directly store the entire wave function and propagate the circuit and simulate the whole thing. And this is actually very fast. That is not exponential time in the number of cycles, for example. But it does require a ridiculous amount of memory. And I said here that it exceeds the amount of RAM that is on Summit, but it does not exceed the amount of hard drive on Summit. So if you can figure out a way to transfer data back and forth between Summit, hard disk, and RAM in a way that's efficient, then you can do it. But nobody's actually done this yet. They think they can do it, but as far as I know, they have not actually tried, because that's sort of a very expensive thing to do. So I would concede that it's if they can get their hands on the machine just to do this specific thing and get access to all the hard drives, it's probably possible. But the other algorithm that we're looking at here is more memory efficient. It fits onto the RAM limits of the Summit machine, but the trade-off is the amount of time. So. But also, as I pointed out, it's been a year, and as far as I know, they have not actually tried to do it. So.
Thank you.
Is Google, like, the relationship between Google, IBM, some other IonQ, like competitors, like, or more collaborational speaking?
I mean, I would certainly say we are competitors, but I mean, there are certain like things that we are all a part of, and we all want to see the field sort of succeed, right? For example, there's something called the Quantum Economic Development Consortium, I think, which is a bunch of industry groups together to try to figure out what's the best way to develop the quantum workforce in the United States, for example. And we also all go to the same meetings, for example, like the APS March meeting, and we'll give talks there and exchange ideas there too. But certainly, at least some part of the relationship is competitive.
So if there's any more questions? So I think we can end here. So thank you, Jimmy, so much for giving us this really like fruitful talk, and it's sort of very good materials and richful. And this recording will be uploaded to DuQIS YouTube channel, so you guys can just check out DuQIS Duke for the entire video. And yeah, feel free to reach out to us, like DuQIS member, at any time if any questions. And we'll be having a house course next semester. And if any of you is interested, please just register for it. And yeah, thank you, Jimmy.
Thank you so much.
Thanks, everyone.
Before we drop off, just really quickly, I was just wondering if you do want to get in touch with you, Jimmy, in terms of the work you've been doing, how could we do that?
I have an email on the first slide. It's chenjimmy@google.com. But
okay. Oh, perfect. Thanks a lot.
Yep. Okay. Thank you, everybody.
Yeah. Thanks, everyone. Have a good day.